So today we aim to solve the hydrogen atom problem, as it is called, and this is one of the well, possibly the only real physical system that can be analytically solved, and it has great importance for getting further solutions to like more complicated atomic problems or other systems. So I hope since you all have done the assignment, you are familiar now with the form of the Laplacian in spherical coordinates. So that we will use. In the last few classes, we've been talking about the angular momentum operator. We will also use that. And then we will first formulate the Hamiltonian, and then we will go on to solve it. So we will not solve it in a very straightforward manner, I should warn you, because it's still a complicated problem and you cannot just directly go ahead with solving the differential equation. It will involve a lot of change of variables to get it into some standard form of differential equation whose solution is already known. So it's similar to the previous two problems that we've done, the harmonic oscillator and the L square eigenvalue equation. So let me just recap the Laplacian operator in spherical coordinates. So this is the R part of the Laplacian, and then you have the angular part, which involves the two angles theta and phi. And we have seen that the L square operator, that looks like minus h cross square, and something very similar to the angular part of the Laplacian, which is 1 by sine theta del del theta sine theta del del theta. So basically, except for the h cross square factor, and the r square over here, the L square can be directly replaced in the Laplacian. So I can also write my Laplacian operator as 1 by r square del del r square del del r, plus 1 by r square L squared by minus h cross. So now you already see that there is an advantage to using the L square operator, because we know the eigenstates of the L square operator, and we'll make use of it in the Schrodinger equation. Okay. And the
Ma'am,
yeah,
ma'am, there it should be a minus h bar square, right?
this one, yes, this is minus. Yeah, this is minus. Okay. And what
Why
else
have
had we?
hat on the Laplacian? Isn't it just the normal Laplacian, or is it some quantum version of that? Like,
It's the normal Laplacian.
okay.
I mean, it's a differential operator, so you can put the hat on it. So the hats just tell you that it's an operator and not a scalar. So if you don't want to put the
I
hat,
was confused.
yeah, it doesn't matter. Okay. Anyway, now, and what else had we done? we had found out the equation that we need to solve to get the eigenfunctions of L squared. And the equation was ddx, where x was a new variable, cos theta basically, squared dpln L plus 1 minus n squared by 1 minus x squared plm equal to 0. Okay, so this is the equation we needed to solve, but we only solved for n equal to 0. And what we got was that the solutions were the Legendre polynomials called PL, and they had this form according to the Rodriguez formula. Like this. So the solutions could be generated by using this differential operator as per the Rodriguez formula for Legendre polynomials. Now luckily, once you know the solution for m equal to 0, mathematicians have shown that you can generate the solutions for m not equal to 0. So that if you wanted something for m not equal to 0, all you had to do was multiply 1 minus x squared to the power of modulus of m by 2 ddx of to the power modulus m plx. So plx is the solution for m equal to 0, and if you wanted something for a non-zero m, you only had to carry out this operation. Now what this also means, okay, let's think of it a little bit more. So plx was a series solution. It was a polynomial series which truncated at some point, and this truncation point was basically let's say L. So this looked something like ALX to the power L plus AL minus 2 x to the power L minus 2. Okay. So I'm just writing the series now in reverse order, like going increasing in power from the maximum power. And this had a maximum power of L, which means that since there is a differential operator, it will kill anything that has powers of m greater than L. So if m is greater than L, you get 0 basically. So the only valid solutions can be obtained only for modulus of m less equal to L. So you get my argument that since this polynomial stops at L, you can only take derivatives up to m equal to L, modulus of m equal to L. So this means that m, to get solutions to this equation, we can only get it for a subset of m which lies between minus L and plus L. Okay. And of course, what if you have more solutions other than the series solutions that we've obtained? Well, it has also been shown conclusively that there are no more solutions. You only have these, the ones which we have obtained. Now, I'm not going to, well, I myself have never seen this proof, but I believe the maths people when they say this. Okay. So this means that I'm just writing it a little bit explicitly. If L is 0, then you have solutions only for m equal to 0. If L is 1, Then I have solutions for m minus 1, 0, plus 1. If L is L, then, so if I want to write it generally, then m is equal to minus L plus 1 dot 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 0 L 0, 1 up to L, which means that there are 2L plus 1 values of m for each L.
Ma'am,
Yeah?
previously for L also we were finding that we could get both positive and negative values, but we were working only with the positive values. So for M also we work only with the positive values, or we take the negative values into consideration as well.
No, we take it into consideration as well, because the m appeared as m squared in the equation that we solved, which means that the Lz will always be positive irrespective of if you take m plus 1 or plus something and or minus something. So it's always a valid quantity. But for L, since we wrote it as L into L plus 1, we had to choose only the positive ones, which would again give me a positive L squared. Yeah, for M we take both positive and negative. The short
Okay,
answer
ma'am.
is that. Yeah. Okay. And then, so the combined solution for the function of theta and phi, which I don't know if I wrote y before. The combined solution
Are
for
these
the
L
angular
and M
part.
the same? Are these L and M the same we learn about in school actually? Are these the same?
Yes, they will turn out to be the same. Yes.
Okay.
Yeah. So this is the azimuthal quantum number and the uh, magnetic quantum number that you learn about in school, the hydrogen Bohr's model and all that. The source, of course, is in quantum mechanics. And the experimental evidence was the splitting of lines. But yeah, so they corroborated each other. But all these rules, they came from quantum mechanics. So what we're doing now. Okay, so the solution for the angular part then involved, we had taken this product, right, IM, and then we had PLM, which is a function of cos theta. And then this, of course, this can be, you can put a normalization constant in front of it. We will not solve it. You don't need to look at it. But for completeness, I need to write it, which is basically 2L plus 1 by 4 pi L minus m factorial by L plus m factorial. And I need to put a minus sign. Some space. Minus 1 to the
Ma'am,
power.
actually your
Visible.
screen is stuck.
Ma'am, the screen is
Oh,
lagging.
okay. Gives me some time to write it. Yeah. So I'm writing again. Can you see? Hello?
No, ma'am, we can't see anything written after
Okay.
YLM.
Okay. So maybe I'll just stop sharing and share again. That will solve the problem. Yeah, can you see now?
Yes, ma'am, we can see it
Yes,
now.
ma'am.
Okay. So remember we had taken a product function for phi and theta. We had separated the two variables. So, and the solution for the m part was this e to the power im phi, and then we obtained the solution for plm. So that is this form that I have written right now. And when you normalize this, so by normalization I mean theta goes from 0 to pi and phi goes from wait, what was it? So phi goes from 0 to 2 pi and theta goes from 0 to pi, I think, yeah. In that angular space, you can normalize it, and this is the normalization constant you get. And the overall function, so this is the function when m is positive, so from 0 to L, and if m is negative, then your solution has it's just a little bit this is L minus m theta phi, and you take a complex conjugate for m less than 0. So this is the final solution for the angular part. So if you replace m by minus m in the first equation and you then take a complex conjugate and then put another sign, then you will get the solutions for m negative. Now this is not something you want to remember or use very often, but since this is a general quantity and it is applicable to L, this is L comma minus m, which means it is the function
Ma'am,
for,
in the factorial for the square root, that one.
this is L plus m. L minus m in the numerator and L plus m in the denominator. Okay. Fine. So this is these are called spherical harmonics, and they apply to all spherically symmetric systems. So that's why they are very important, and if you have a spherically symmetric system, then this part of the wave function always gets separated out like it did in our case. So that's why it's important to know that know the form of these functions. Okay? But you seldom have to use them. In most cases, they would get integrated out. Yeah, that may not make sense to you now, but you will see if you try to do a problem or a particular physical system, this part will normally get integrated out, and you seldom have to use this explicit form. Okay. So just the properties of the spherical harmonics, the YLF, they are usually sufficient to deal with any system. Now, the most important property, of course, is that YLM form a orthonormal set. So, which means if you have L prime M prime not equal to Lm, then the overlap is 0. And if you have, and for like equal, you have overlap equal to 1. Yeah, I'm not going into this much because you will not use it so much. And then I'll just give you some examples to show you that not all the functions look so horrible. So if L equal to 0 and M equal to 0, then Y00 is simply 1 by root of 4 pi. Then if you have y L equal to 1, m equal to 0, then it just looks like 3 by 4 pi cos theta. And if you have L equal to 1 and m equal to plus minus 1, that is minus plus root of 3 by 8 pi e to the power plus minus I phi.
Is this normalization done over like the volume? I mean, what is it normalized over?
It's normalized over the solid angle basically. So the whole angular part for a,
Is that why there's the 4 pi in the denominator there?
yeah. It's over the solid angle basically. So this is about it for the spherical harmonic. So this is the angular part and we found the angular part. Now we need to find the radial part. And the radial part of course is different for different spherical systems or spherically symmetric systems, and it depends also on the potential that the system is subject to. So now we go to a specific case, which is the hydrogen atom. Okay. And we will solve the Schrodinger equation for the electron in the hydrogen atom. Psi. And this is equal to square by 2m. So this is the kinetic energy of the electron, and it has a nuclear attraction potential. So this is the nuclear attraction of the electron. So this is an attractive potential, and it only depends on the distance from the nucleus. So that's R. So in general, a potential can be written as a function of the position, but this is the position vector. So it may depend on the angle of from the origin, etc. Not only the distance. But if a potential depends only on the magnitude of the distance, then it is called a central potential. And the analysis that we did before, the whole, whatever we've been doing in building up to the hydrogen atom, they're valid only for central potentials. Because if the potential depended on had some angular dependence, then introducing this would again mix up my r theta and phi, and the separation that I had done before would no longer be applicable. Now let's continue. So I'll have to write the Hamiltonian a bit more explicitly. That is minus h cross square by 2m r square. So it's whatever I wrote before. Del r plus 1 by r square plus h square. Okay. I'll change the form a little bit by doing one derivative. So I will. So this is the same as 1 by r del square r del. Okay, then put a psi here. Then it will look better. Square. R square. Okay, so this, so I have converted this to this form. You can verify that it's the same actually. So all you need to do is carry out the operation of this derivative on the quantity in brackets, and similarly do the second derivative on the quantity in brackets, and you will get the same thing. Then, so this is the form of my Hamiltonian, and I know that the form of my wave function. Now this has both.
But we get a factor of 2, right?
Here, no, that so you will.
I mean,
get,
the original one, there is a factor of 2.
In the original one, no. So you will get 2 terms from the first one, and again 2 terms from the second one, and they're both the same.
Okay.
So you, yeah. So when you do this second one, okay, you will get 3 terms, and 2 will be the same, and those 2 will add up to give you the 2 containing term in the first one. You can try it out. I verified it just there. So I am sure it will work out. Okay. Yeah. So what I was saying is, then the wave function. This has both a radial and an angular dependence. So I'll write the radial part as r of r, and this is the angular part y theta phi. And you can see that when I substitute this into the Schrodinger equation, something very nice will happen. So this first term depends only on r. Okay, so it will only act on the capital R. The angular part will just remain as it is. Now here you have the operation of the L square operator, which operates only on the angular part and gives me an eigenvalue into the angular part, right? And here this is just a multiplication. So if I do that, I can write by r squared r squared. So I can, okay, I'll write the y's for now, and then you cancel them. Then we have 1 by r squared. So L square operating on y LM will give me L into L plus 1 and give me back psi. Okay. And then I have VR Ry is equal to ERY. So then I can remove y, and I end up with a purely radial equation.
Ma'am, how did you get the L into L plus 1 there? I'm not understanding that.
This was the eigenvalue equation for my L square. So
Oh, okay, okay.
minus h cross square L into L plus 1 y. Okay. So we use this. Yeah. So now I get only the radial equation, and then I have 1 by r squared L into L plus 1 into r plus v into r, which is equal to E r. And this is now what we want to solve. So the other thing you will now notice is that the energy depends entirely on the radial part of the solution. So and at least apparently. So the eigen function is just r, but it also has, remember, the small l. So the energy will depend on small l. but this equation does not contain any m, so it will not depend on any m. So we can already see that E depends on the on RR and the value of L. We can already see that, which is an important thing. Now we will entirely focus on solving this equation. Okay. So what will we do? So since we have an RR here, and we have also some R's in the denominator, people thought it wise to multiply R. Now again, all this has been arrived at by lots of trial and error. So if you ask me, can you tell me why we're multiplying by R by just looking at it? I can only give you a vague answer like, okay, it will remove some R's from the denominator, we have this RR in the bracket, but actually it's not so obvious to anyone until you work it out and you see that multiplying R actually helps. Okay. So this was quite a lot of painstaking work for a lot of people. So if I multiply by R, and you are only learning the quickest way to the solution. So 1 by R square, L into L plus 1, RR, B into RR, equal to E into RR. Okay. Now I will replace RR with another function, which I will call U of. This, I guess, no one opposes. It's just simple. Let UR to this. Then I get minus H del square U del R square plus. So I'm also opening out the brackets now. Plus H cross square by 2m 1 by R square L into L plus 1 plus R. So this is a that's just confusing.
Oh, ma'am, your screen is freezing.
It's frozen. Okay.
Yeah, it's frozen.
Let me. Okay, it's frozen. What can I do? I'll have to again stop broadcasting. Then again start broadcasting. Yeah, okay. So I've replaced RR with U, and I've opened the brackets. And now I have a differential equation where there is a second derivative in the first term, and I have two potentials multiplied with U. Okay. And out of the two potentials, like I mentioned, so V is an attractive potential. It is the nuclear attraction for the electron. And this one is a positive quantity. And this is a repulsive potential. And it is related to the fact that the closer the electron comes to the nucleus, the faster it needs to revolve around the nucleus for stability. So it is related to that. But the fact that this is repulsive potential, you can see. So L is positive and there's R squared. So this is repulsive. And V has the form minus ZE by R, so that's an attractive potential. Now,
Is it like the centrifugal force, like the quantum version of that?
yes, yes, that is right. I didn't want to mention it for fear of people asking me what that means quantum mechanically, but yeah. But for the solution purposes, what is important is that it is a positive. And then we have hello? Yeah, hello, sorry. So yeah, so I was sharing my screen. So from this, we're defining an effective radial potential, which we can call V effective R, which is basically this. And I'll try to draw something. So now I'm plotting V versus R. So the attractive potential, it goes as 1 by R. It's a Coulomb potential. That goes something like this. And then this repulsive potential, it goes as 1 by R squared. So it will drop off faster. Okay. So this is V of R. And this is, I don't know, I can call it A of R if you like. And then the net potential then will look something like this. So at long distances, it will merge with the Coulomb potential. And in the middle, there will be some sort of balancing act, and we'll end up with a plot that looks like the Morse potential or the usual potential energy surface that you have and that you've probably seen in school for the hydrogen atom. Okay, and in this minima, you will end up with certain bound states. See, these are quantized bound states. And our target solutions will be actually these quantized bound states. Now, let's just go back to the wave function again. In terms of u, this is a function, u is a function of r, and then it's r, and then you have y lm theta phi. So this is the form. So, and from the dependencies in the Schrodinger equation, you see that u depends on the energy and some number L, the quantum number for the L square operator. So you have to keep that in mind. The u will contain the u should be related to both the energy and the value of L for which we are carrying out the solution. And then let's just finish off with the normalization of psi at this point. There's not much to say, but it was a question from you that what happens. So the normalization that you need is basically this, that the full wave function should be normalized over all space. So this is a volume element. You write it with a vector, and you can also write it as dq bar if you like. And this translates into an integral from 0 to infinity over r squared dr. So this is again in the spherical polar coordinates. And then the rest of it is integrated. Either you can do it over the solid angle, like I mentioned, or you could split it up into sine theta d theta d phi and put 0 to pi and 0 to pi. And you have one more part that is now u square by r square. So that should go over here, right? You have mod u squared by r square. The r square cancels. And we know that, well, I have said so, that YLM form an orthonormal set. This is basically equal to 1. Equal to 1. So effectively what you need to do is normalize the radial part of the solution u from 0 to infinity, and that will give you a normalized psi, because we have already taken care of the angular part. So our conclusion is that u can be normalized independently. So just to recap, the Legendre polynomials, they involve some sort of mathematical normalization, which is called normalization, but you can maybe call it regularization or whatever, where you choose the form of the solution which gives you a PL of 1 equal to 1, and but that is just the mathematical part, got nothing to do with the physical system. Then when I introduced this very complicated factor with the L plus m factorial and the L minus m factorial over here, this one. This is the true normalization over the solid angle or the angular space. And once that is done, then the radial part can be independently normalized. And you get the final normalized wave function after that. Okay. Now, we are looking for the solutions of the hydrogen atom which are in this minima. So what we are looking for is the bound solution, E less than 0 solution. That is bound state. So for that, what is the what do we need to do? So we need to solve minus h cross square by 2m d square dr square plus what's the h cross square here?
But in the harmonic oscillator and in the particle in the box, we always said that E must be greater than 0 for any solution. Here we are saying the exact opposite.
Yes. So why is that? Because there the potential only gave you some walls or boundaries to the particle, and the particle basically had a potential energy of 0 and a kinetic energy which is always positive. So the energies were always positive. And
Okay.
in this case, there is a potential already which is attractive, and the convention is to define the 0 of energy at a point where the nucleus and the electron are infinitely separated, which means that all the other energies are negative. Yeah. So those, so in harmonic oscillator and particle in a box, they were just what is called confining potentials. But here, this is an actual attractive potential.
Yeah.
Okay. Yeah. So I'm just repeating this again. And now I am writing the actual form of the Coulomb potential. And I'm including the Z to include hydrogen-like atoms. So hydrogen-like atoms basically means you have, the nucleus can have any charge, any atomic number, Z, but you only have one electron in the system. So introducing the Z doesn't cause much trouble, so we solve for hydrogen-like atoms all at one go. For hydrogen itself, Z is equal to 1, of course. Okay, and we need to solve this for all values of L. Now, step 1. Step 1 is we want to go to unit-free variables. So to do that, we're going to shift from R to A0, which is the whole radius, into X, which is unit free. Okay, so we are shifting the units to the scaling factor. And if we want to remove the Z as well and simplify further, you divide by 2Z. Okay. It's just what has been found to work. Okay, 2Z. And then X is a unit free quantity. And if you substitute this and work it out, I will not do this. I don't want to waste time. What you should end up with is 2Z squared E squared by A0 as a common factor, and we get D squared dx squared and then 2 plus 1 by x squared minus 1 by x u equal to u. And this has units of energy. And the operator inside is unit free, which also means that I can shift this quantity to the right and obtain a unit free quantity on the right hand side as well. That is, my equation becomes entirely unit free. And again, like done before, I will write it as kappa square u, where kappa square is equal to minus EA0 by 2Z square. So here we've already ensured that we're looking for negative energy. Okay. Case kappa square is positive and I've put a negative sign. So now basically solving for energy means finding the values of kappa. I think maybe we only have 5 minutes. So I'll stop here for now. Next class we will. So do you all have classes after this?
Yes,
Can I
ma'am.
have? Okay, you all have classes after this. So can you all give me half an hour sometime on Saturday?
Ma'am,
just have
actually, we have a Viva, we have an exam on Saturday, Sunday. Next week
Already an
again, we
every
have
day.
extra
submissions
class.
and Vivas.
Okay, okay. So I have just a little bit left to finish my part of the syllabus, but today it's already 6 o'clock. Um, so do you? Okay. So what I can do is this last part. I can give you a little bit of notes. If I am able to find time or if I'm available on Tuesday, I will finish it. But I'm not sure. Okay. So I will. Otherwise, I will just send you this last 2 pages. Okay.
Or can Professor Pal cover it for us?
He can, I guess, but it would be nice if I finished my
If
section.
it is not
He may
possible for
not.
you.
Yeah, if it is, but the thing is that I have been deriving it in one way. Then he has to go through my full derivation and complete it accordingly. So this is just the
Yes,
last
ma'am.
part.
Because I think Srishti also said it in the chat box that it will be difficult to understand it by reading it. I mean, directly.
Okay. Okay, I can do one more thing. I can teach it and record it and upload it. What do you think? And then you can ask me doubts if you have any. Yeah? For the last maybe 10, 15 minutes maybe.